Okay, I have used my sophisticated artistic skills to draw a petri dish. Okay, 2 petri dishes. So I'm going to give you a scenario and show you how exponential growth and decay plays out in a pretty normal situation. Okay. So here we go. We're monitoring a petri dish and a bacteria population in it over time. All right. So when we first start out with our little colony of bacteria, we count through some unknown method of precisely counting bacteria that there are 5,000 bacteria living in our petri dish. Okay. Half an hour passes, and when you come back using your same very precise method, you count that there are 20,000. See, can't you see? There's so many more bacteria in that, because that's totally what growing bacteria looks like. Anyway, now, assuming natural growth and decay, I'm going to give you 3 questions, so you might want to jot this down apart from these details. Okay. Number 1, assuming natural growth, can you find the population as a function of time? You find the population, let's call it P, right? And our function of time, let's call our unit, let's go with minutes. That's a nice easy unit to go with. Okay? So there's our first question, find population as a function of time. Number 2, can we find the time at which the population will hit 100,000? Okay. When is it going to get to this population size? Okay. The third question has just 2 parts to it, which are very, very similar to each other. These are about the actual quantity, right? But one of the big things about exponential growth and decay is not just what the population is, but how fast it's growing or decaying. Okay? So question 3 is about the rate of the population's change. Okay? We want to know the rate at 2 particular points. Number 1, or part A, after an hour. Okay? What is that rate? Okay? And since we're looking at bacteria and minutes, then our rate will be in terms of bacteria per minute. Okay? So what is it after 1 hour, and what is it when there are 50,000 bacteria? Okay, so we're going to find the function. We're just going to find, okay, how long does it take to grow to a certain size, and then we're going to have a look at the rate, try and get it at a couple of different spots. All right? So, how do we set this out? Well, the first way we start is we say, this is question 1, right? Assuming natural growth. Now, the question may say that to you, as I did earlier on. But sometimes the scenario will not. And based on the kind of situation they give you, for instance, a population growing, or some radioactive substance decaying, okay, you have to assume, all right, this is the kind of scenario that they've got in mind, so you would include in your answer, assuming natural growth. Okay. Now remember, the whole definition of natural growth is that the rate of change is going to be, what was that key word? Do you remember? It's in a ratio with the quantity, but what was the word we used? In proportion, right? So we're going to have our rate of change, so that will be dp on dt, okay? And that's going to be equal to the population multiplied by some constant. Okay, now, by the way, you may have seen in the previous example I gave you, okay, that this k is just a constant, right? So it could be a whole number, it could be a large number, or it could be a small number, it could be a fraction, okay? So it doesn't actually matter which side you put the k on. And just sort of second guessing myself, I think it might actually be more helpful for us as we solve this to put the k on the other side. You'll see why in a second, okay? So really these equations are equivalent. They're still proportional, okay? But this will just work neater for the algebra in a second. Okay? Now, being that this is the kind of proportion we've got, therefore the kind of function we're talking about is an exponential, right? So you can say, therefore, p is going to be equal to, and this is what I gave you before. Okay, now we're going to nut out what these 2 bits and pieces are, but I need to say, I should have set up here, k is a real number. Okay, usually they specify k is positive. And here, I'm introducing another constant, so I should say a is a real number. Alright. Now, with these two unknowns, okay, I'm going to use the information in the question to work out what they are, in very much the same way that you use, like, say, initial conditions to work out what, like, the constant of integration is in a motion question, okay? So, using this as our starting point, and these pieces of information here, okay, how am I going to work out what my A and my K are? Well, we'll start with A, alright? So, based on the initial conditions, okay, they tell you that the population starts at 5,000, right? So therefore 5,000, that's the P, population. That's equal to A, E to the K. Now, time for initial conditions is 0, right? So multiply by 0. Are you happy with that? Now you can see what's happening here, right? E to the, that K becomes, you know, doesn't matter, so it's trivial. E to the 0 is just 1, right? So this part just sort of factors out of the equation. So therefore A is actually just our starting population. Now for this reason, instead of A, even though that's the way the textbooks will say, you'll often see instead of A, in this case we've got a population P, so sometimes you'll see this called P naught, okay? As in the population at time 0, okay? Sometimes when you're dealing with a radioactive substance or something else that's decaying, okay, because you're dealing with mass, instead of P you'll have M, instead of P naught you'll have M naught, okay, so get used to that. Instead of A e to the KT, you could just as equally have written P naught e to the KT. And for you that's just a signifier. Okay, that coefficient there, that tells me where I start. Alright, so now I can rewrite my equation for the population. P is equal to 5,000 e to the KT. Okay. Now, the other constant we have to get rid of will be from the other condition that we know, right? So after half an hour, it's quadrupled in size. So what kind of equation can I form? What should I write? We got this one out of our initial conditions, right? So the two bits that we know that we're going to input in are, number one, the time, and number two, what the population is actually equal to at that point. And just as a side note, we didn't have to choose minutes. We could have done hours, right? And time would have just been 0.5. No problems. You come up with exactly the same answer. But we just sort of pick our units so we get nice numbers, integers, that kind of thing. So I'm going to say, well, the population at this point is now 20,000. Okay. Don't need to say A anymore because I know exactly what A is. That's 5,000. And this will be e to the power of, now, kt. T is 30. Right? So therefore I'm going to put in 30k up here. We want to make k the subject, so just a little bit of work to get there. Let's divide through by 5,000, so that gives you 4. You're e to 30k. So now that I have k in the right, you know, up here on its own is the only value left. How do I rewrite this? How do I rearrange? Good. So exponential equation to a log equation. The power becomes the subject, which is the whole point. You know, that's why we're rewriting it like this. Okay. This base here becomes the base of the new log, right? So this is log base e. This is natural log of the only other number that's left, which is 4. So if you want k, therefore what you have is 1 on 30 log 4. Okay? Or log 130, that doesn't matter. Okay? So that's all the pieces we need. Let's just tie it all up in a nice knot. There's my k, there's my a. Therefore, the population can be expressed as 5,000 e to the... Now, with k, remember we called this k the constant of proportionality. So this tells you where you begin. Okay? This tells you how fast you grow. Okay? So it has the effect of stretching things out. Do you remember when we were graphing, you know, say e to the x versus e to the 2x or e to the 3x? Okay? What's the difference between all of these? Okay? Well, when you think about it, if you put e to the x here, okay, changing that index will make it still go through, it's still got the same intercept, right? But it's going to grow faster and it's also going to decay faster, right? Sorry, it's a bit wonky, but you're getting the idea. And that would be 3x, right? So whether you're decaying or growing, everything will happen faster. So that's what this number here defines, okay? How do things go from one to another? Which is why we use this condition and this condition together to come up with this number, okay? So therefore, I'm going to try and keep it together. So rather than writing, up here I've got kt, right? Rather than writing t on 30 log 4, I'm going to keep that as one thing. It's a really important number, and I want to highlight it on its own. So I've got 1 on 30 log 4 t. Okay? I mean, it doesn't really matter where you put the t, but I think that's a helpful way to write it.